Hi everyone, welcome to Build and Learn with Chi. The current Build and Learn project is a loudspeaker system. In our last video, we talked about sound waves. Please watch the video here. We learned that sound waves are created by vibrations and that they need a medium to travel in, such as air, water, or solid. Today, we're going to be learning how to get those vibrations started in our loudspeaker with the use of electromagnet. Magnets are substances with invisible magnetic fields. Now, when other magnets or some metals with magnetic properties are placed close to this field, they experience a force. The force can be an attraction or a repulsion. Magnets usually have two poles, North Pole and the South Pole. When two like poles, say North and North or South and South, are brought together, they repel. On the other hand, when two opposite poles, say north and south, are brought together, they attract each other. Now, permanent bar magnets, like the ones you may have used in school, are often labeled with N and S, specifying the north or south poles. But how can we tell which is the north or south poles in an unlabeled ferrite magnet, for instance? Well, a compass can help. A compass needle usually aligns itself with the magnetic field of any magnet. The end of the needle marked N points towards the magnet's south pole. Using a plotting compass and a permanent bar magnet, we're going to be demonstrating how to identify the poles in any given magnet. So in this demo, when the red colored end of my bar magnet is brought close to the compass, we notice that the compass needle turns and aligns with the S point on the compass. That tells us that the red end of the magnet is the North Pole. Why? Because like poles repel each other. The end of the compass is being repelled and swings to point south, meaning it's near another North Pole. Now when I rotate the magnet and bring the blue end towards the compass, the needle aligns with the end point. That means it is the South Pole because opposite poles attract. The end of the needle is being pulled towards the magnet. Permanent magnets are usually manufactured to a certain specification, such as desired field strength, size, and even the shape. But what if you wanted to create your own magnet with your own unique specification? Could you do that? Well, yes, that's where induced or electromagnet comes in. When electricity is made to flow through any wire, a magnetic field is usually created around the wire. That's what we mean by electromagnet. Electricity flow inducing conductors to have magnetic property. Now, for straight wires, the magnetic field is usually concentric or circular in nature. We can actually verify this using a simple demo. In this demo, we have connected a copper wire using crocodile clip to a power pack. We then turn on the power pack to allow electricity or current to flow through the copper wire. When a compass is brought near the wire, as you can see, the needle turns frequently, indicating that there is a magnetic field around this wire, and the needle turns to align with the circular magnetic field around this straight wire. To make an electromagnet even stronger, we can take a straight piece of wire and then wind it many times to make a coil. This is called a solenoid. Now, when we place an iron core or an iron material inside the solenoid, the magnetic field around our solenoid becomes a lot more stronger and much more powerful. With it, we can attract magnetic objects such as a paper clip, for instance. Now, unlike the circular field around a straight wire, the magnetic field around a solenoid looks just like the field of a bar magnet, with the north pole at one end and the south poles at the other end. Now, if we place a compass near the solenoid and run current through it, we can see the needle deflect at each end, proving that the solenoid itself produces a magnetic field with the poles at each end. We define current as the flow of electrons. Now, here is something important to note. Electrons usually flow from a negative terminal to the positive terminal of your power source. However, in engineering, we usually use the conventional current instead. Now, what does conventional current mean? Conventional current simply does the opposite of how electrons flow in reality. Conventional current flows from a positive terminal to a negative terminal of your power source. Now, why have we brought this? Because we're going to be applying the conventional current rule to our electromagnet. Now, we use conventional current when talking about the right hand rule, as shown in the image above. The right hand rule says when you coil your fingers of your right hand in the direction of a conventional current in your coil, your thumb points to the solenoid's north pole. And what happens if I change or reverse the connection? If we reverse the connection, the direction of the conventional current changes, and so does the magnetic field. That means the solenoid's north and south poles would switch places. Now, applying the right hand rule again, we see that my thumb is on the other side, therefore, that side is the north pole. With direct current or DC, current flows in one direction only. So if I wanted to flip the poles, I would have to manually swap my wires connected to the power source. However, with alternating current or AC, like the electricity from your wall socket, the current naturally reverses direction many times per second. That means the voltage at each terminal constantly alternates between positive and negative. And because of this, a solenoid powered by an alternating current power source will have its magnetic poles flipping back and forth in sync with the alternating current. Now, what happens if I place an electromagnet or an induced magnet in the magnetic field of a permanent magnet? Really interesting things start to happen. The current carrying wire will experience a force, which is a push or a pull or motion, depending on the polarity and if it is placed at right angles to the magnetic field. This is known as the motor effect. The size of the force produced is dependent on the current flowing through the wire, the length of the wire, and the magnetic flux or strength of the permanent magnet. The formula to note is F is equals to BIL. Now, based on what we have said earlier, solenoids have poles at each end. Now, these poles could either be attracted to the magnet and move down towards the magnet, or be repelled by the permanent magnet and move away or move up from the permanent magnet, depending on the direction of the current flowing through the solenoid. Alternating current, which is the current that comes into our houses and our sockets, changes direction as we mentioned earlier every time. It could go from positive to negative every time. Therefore, the direction of conventional current would change correspondingly. It means our electromagnet could simply be moving up and down each time. We're going to be introducing the Fleming's left-hand rule to show the direction of the force when the current flows through a solenoid. In Fleming's left-hand rule, the first finger is pointed in the direction of the field. The second finger indicates the direction of the conventional current. Now, your thumb stuck out at right angle shows the direction of motion or force. When conventional current changes direction as AC current frequently does, Fleming's left-hand rule, when applied, shows that the thumb, which is the force or motion, facing downwards, with this change in conventional current flow correspondingly. We would use a demo to illustrate the motor effect. Here, I've connected a single piece of wire to an AC power source and placed it on top of a permanent magnet. Because the current keeps changing direction, The direction of the magnetic force on the wire also keeps changing. And then sometimes the wire is pushed upward in response to that, and then other times it is pushed downward, being attracted as the case may be. As a result, we see the wire oscillating back and forth. Remember, very fast oscillations are what we call vibrations, and this is the same principle that gets vibration started in loudspeaker. Now, when those vibrations pass through a material medium, and then there's some good resonance, we hear the sound as it gets amplified. In our next video, we would outline the equipment needed and the key parameters we're going to calculate beforehand, and then we'd start building our loudspeaker. If you've enjoyed the video, please show support by subscribing, sharing, and also liking. Thank you. See you next time.